Am I audible, everyone? So, good afternoon, everyone. So, in today's class, we'll briefly recap what we discussed in our last lecture. So, in the last lecture, we have seen what is an MDP, and we also seen the definition of what is a value function and what is a action value function, right? So, what is a Markov chain? Do you remember? So, what is a Markov chain? A, a sequence of random variables are said to be a Markov chain if the probability of ht plus 1 probability of ht plus 1 given ht minus 1 so on is same as given ht. So the future will depend only on the past, like only on the present, right? Conditioned on the present, the future is independent of the past. So then what did we see? What is MDP? What is the difference between a Markov chain and an MDP? In Markov chain, you will be in some state with some probability you move to the next state. In an MDP, you have some action to take, right? So an MDP is defined like this, right? This is a Markov chain. What is an MDP? An MDP will be having some set of states and actions. And we talk about what is the probability of st plus 1 equal to s dash and rt plus 1 equal to r given. This is what uh, defines the dynamics of a Markov chain, right? Markov decision processes. So we have some state space, so we have some action space, and these dynamics tell us if you are in some state S and take an action A, with what probability you'll go to S dash, and what is the reward that you get. And we also discussed this concept of discount factor. Do you remember what is discount factor? So what is the definition of a return? What is called return? So return is GT equal to, right? This is nothing but the total future reward that you'll get starting from time t. And what is episodic MDP and what is continuous MDP? We have seen what is called episodic MDP and continuous MDP, right? What is that? The episodic MDP terminates when we reach some particular state called a terminal state. The continuous MDP keeps on going, so there won't be any state called terminal state. Okay. It stops at this terminal states. No such terminal state. And what is discount factor? Why is it useful? So GT can be unbounded in the continuous MDP setting, right? Because there is no such stopping state. It will go on forever. So you are summing all the rewards till infinity. So your GT can go unbounded. So to prevent that, we take discount factor, which gamma belongs to 0 or 1. And you define your GT as what? Gamma power Ri, right? It's like gamma RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3, so on. Okay. So if gamma is less than 1, this will form a decreasing series of GP, so it will converge. Okay. What else did we discuss in last lecture? So what is value function? What is value function? So this is the expected total cumulative reward that you'll get if you start from status. So how do you define that properly? Expected value of what? GT given ST equal to S. What is the action value function Q pi? What does it mean? You started some status and you already decided that you're going to take action A, and from the next step you will follow policy pi. Okay, so what does that mean? Expected pi GT given ST equal to S, AT equal to A. We also seen how to write V pi in terms of Q pi, right? How can we write? Can we write like this? What should I multiply? Pi of fine. V pi is telling every step, every action should be taken according to pi. Q pi is telling, okay, first action I'll take according to A, and from second next action I'll follow pi. So we are just saying even the first action should be followed according to pi. Then we'll get V pi. Okay. So this is what we have discussed in our last lecture. So in today's lecture, what we'll see is, the topics that we'll see is, we'll define what are called Bellman expectation equation. So if you have some policy pi, if you want to understand how good is that policy, so what do we need to find out? So how, if you want to say how good is a policy, how do you measure the expected return that that policy will give, starting from some status? If you look at all the states, for every state you'll have some expected return if you're starting. So you just look at that vector. If you start from state S1, what is the expected return I'll get? If you start from state S2, what is the expected return I'll get? So that's what will measure the performance of a policy. So V pi of S essentially measures the value of a policy. Okay, how good is a policy is measured by V pi of S. Okay, so if you want to find V pi of S, I'll give you the dynamics of the MDP. I'll tell you all the transition probability matrices and I'll essentially give you this dynamics, this MDP dynamic. How can I measure V pi is one thing which is of interest, right? If you have two policies, if you want to say which policy is good, you should know how to measure the performance of a policy, right? So this Bellman expectation equation will help us find how good a particular policy is. In some sense, it will give you a way to find V pi of S for a given MDP and a policy. If you give me an MDP and a policy pi, Bellman expectation equations will tell me how to calculate V pi of S. Okay, this will be useful to find V pi of S. Okay, so we'll see those equations in today's lecture, and then once we know how to define the performance of a policy, if you want to talk about optimal policy, how do we define an optimal policy? The the performance of a policy is given by V pi, right? So what could be the definition of an optimal policy? A policy pi which maximizes V pi. So we have to we'll see the definition more carefully, because V pi is a vector. It's not a scalar, right? Because for every state you have a V pi of S for every state S. So it's not one particular number, it's a vector. So we have to define the optimal policy carefully. Okay. We'll see the definition of an optimal policy. Okay. And we'll also see under what conditions even an optimal policy exists. Okay. And so, as I said, Bellman expectation equations are useful to find. If you give me some policy pi, it will tell you how good is that policy, right? But that's not what we are interested in, right? Finally, we are not interested in understanding how good is a particular policy. We are more interested in finding an optimal policy, right? So, Bellman expectation equation is just useful to evaluate a given policy. But if you want to find an optimal policy, there are another set of equations which will be useful, which are called Bellman optimality equations. So this is useful for what? What are Bellman optimality equations useful for? To find pi star, to find optimal policy. Okay. Yeah. So these are roughly the topics that we'll cover today. So let's start with understanding what are Bellman expectation equations. So I'll define a few notations which will be useful for us to define this Bellman expectation equation. So we assume that we know the dynamics of the MDP while doing this. So what do we mean by knowing the dynamics of the MDP? We know this. We know this for all S, S dash, A, R. We know this for all S, S dash, A and R. Okay. This we know dynamics. We know this dynamics. Now we'll define the following. So if let's say we have some policy pi, next state. So if you have some policy pi, what is the probability that if you follow policy pi, if you follow policy pi, what is the probability? And if you are in some state S, and if you follow policy pi, what is the probability that you'll go to some state S dash? I'll just denote it like this. Okay. If you are in some state S, and if you follow policy pi, what is the probability that I'll go to some state S dash? So this is what I'll write it like this. Probability that st plus 1 equal to S dash given st equal to S, and I follow policy pi. Okay. So can I compute this from my knowledge of the dynamics? How can I compute? So first of all, I have P of S dash R given S comma A. Uh, can I find this thing from this from this? Can I find this? How? Just integrate over, right? This will give me this. Then if I know this, how can I find P pi SS dash? It is sigma over, let's say the finite set of actions, sigma over all A, P S dash given S comma A into what should I multiply? Pi of A given S, right? So I know how to find P pi SS dash, right? If you are in some state S, and if you follow policy pi, if you take the action according to pi, what is the probability that I'll go to S dash, right? So this is giving, if I take action, I go to S dash. Fine. Okay, sorry. So this we know. Can we also compute this thing, which is R pi S dash, which I'll define as R pi S, I'll define as expected value of RT plus 1. If I follow policy pi, what is the expected value of the immediate reward that I'll get when I'm in some state S? I'm in some state S. I'll take action according to policy pi. What is the immediate expected reward that I'll get? I'll define R pi S like that. Okay. So can I compute this? How can I compute? What is the expected reward that I'll get for taking some action according to pi? I know this, right? Uh, I can calculate this, right, from my joint distribution. From this, I can calculate this, right? I just marginalize. I just marginalize over all future states. Then if I'm in some state S and take action A, this is a reward that I'll get. But this is not what I want. I am taking my action according to policy pi. So then what is the expected reward that I'll get? So if I just do this, what will I get? This is the probability into, is this fine? I should also do, like, first I'll do this. I'll find expected reward for being, if I'm in some state S and take action A. I'll first find this. How can I find integral over R P of R given S comma A dr? Hmm? What R? Yeah, expected reward. Yeah, fine. This is what is the expected reward? Right? I know the distribution. I'm just taking the expected value of the distribution. Right? Expected h is sigma, integral h p h. Right? Integral h p h. That's what I did. Okay. Now, if I have this, how can I find expected R given st equal to s, and I take action according to pi? How can I find this? If I am in some state S, what is the expected reward I'll get? Now I'm asking, what is the expected reward I'll get if I'm in some state S and take action according to policy pi? So how can I get this? Summation over all actions expected R given st equal to s, at equal to a, into pi of a given s. Fine. So this is the if you take action A, but we are taking action according to some probability distribution pi, so we are just averaging it out. Okay. Any doubts still now before I proceed further? It's just a simple expectation and averaging out. Okay. So this is equal to what? How am I denoting this? R pi s. Okay. If you are in some state S and follow policy pi, what is the expected immediate reward that you'll get? Okay. So if you know the dynamics, you can calculate all these things. Whatever you want, you can calculate because you have every knowledge about the MDP. You have all the knowledge about the MDP. Okay. Now what we want to do is, we want to understand how we can find V pi. If we know the dynamics of the MDP, how can we find V pi? Okay. So let's try to do that. What is the definition of V pi? What is the definition of V pi of S? Expected value of GT given ST equal to S. Correct? So what is GT? Can I can I write GT as RT plus 1 plus something? RT plus 1 plus what else can I write for GT? Can I write GT plus 1 here? Correct? Because GT is RT plus 1 plus gamma times RT plus 2 plus gamma square RT plus 3, so on, right? So I can write GT as RT plus the immediate reward plus gamma times GT plus 1 given ST equal to S. Now, if I use conditional, like if I just use linearity of expectation, what will I get? So here it's not, notation is a little bit wrong here. So it should be RT plus 1. Okay. So this will be like expected pi RT plus 1 given ST equal to S plus what will be there? Gamma times expected pi GT plus 1 given ST equal to S. Correct? So what is the first term equal to, according to our notation? R pi s, right? R pi s plus gamma times. What is the second term equal to? Is it V pi of s? Is it equal to V pi of s? No, right? If it was gt, then it was V pi of s, but it's gt plus 1 here. So if you want V pi of s, what should I condition on? I should have st plus 1, conditioned on st plus 1, right? If it is gt plus 1 given st plus 1, then it's V pi of s, right? But right now it's conditioned on st equal to s. So I want one more conditioning. So I'll just introduce that conditioning and just uncondition it. Okay. So what can I do? I want this expected gt plus 1 given st plus 1 equal to s dash, let's say, and I cannot, already this conditioning is there. I cannot do anything about it. But if I introduce one more conditioning, what should I do? I should average it out, right? Just like how we have been doing all. Like we have condition on s, then we have conditional condition. Then what it is that the effect we just averaged over all possible a's. So similarly, we have to do that here. I just conditioned on an additional random variable st plus 1. So to remove that effect, what should I do? Sum over all possible s dash p pi ss dash, right? Is it clear? Why I wrote it? Similar to this. If you understand this part, this is similar, right? Here you had conditioning on s, and the first thing you just gave an additional conditioning on a. Then you just calculated what is the probability of taking that a given s and just summed over all possible a's. Similarly, here you are doing the same thing. Like if you want, I can write it more explicitly. Yeah. What? No, it's applicable for both the settings, both continuous setting and no, V pi of s is definition is what? It's condition, it's GT, right? Whatever is the remaining future reward, that's what we are talking about. No, if you start from a state S, how you came to that state doesn't matter, right? No, we are not assuming that t is finite. T is a random variable, I told you, remember? Or t is a stopping time, which says that if you reach some particular terminal state, you'll stop. So you're talking about till you reach the terminal state. So if you are in some state S, the index, the time index does not matter, right, for you. You are in some state S. Where will you go in the future doesn't depend on what time it is, right? It only depends on where you are right now. So where you will go has nothing to do with what is the current time. So it's not dependent on t. Think of it like a gambling game, no? So you have 5 rupees right now. Whether you have that 5 rupees at 10 o'clock or let's 12 o'clock, it doesn't matter. So you have 5 rupees, you play the game till you either win all the money or lose all the money. So where you start only matters. At what time you have 5 rupees doesn't matter. Because the game is not till some 12 o'clock or something. The game is till you exhaust all your money or you get all the money from the lottery machine or whatever. Let's say maximum you can get 100 rupees. Till you play till you get 100 rupees or you play till you get 0 rupees. You are exhausted all your money. So at some point of time, you have 5 rupees. Now you are asking about what is the total gain I will get. So it doesn't depend on whether the time is 10 o'clock at that time or 12 o'clock at that time. Because you have 5 rupees, you'll play the game till you exhaust all your money or till you earn all the 100 rupees or whatever. So T doesn't come into picture. It just matters on where you start. Okay. Is it clear to everyone? So the total return just depends on what is your current state and what policy are you following. Okay. So at say some t equal to 1, you are in some state 5 rupees. Let's say again at t equal to 10, you come to the same state 5 rupees. So your probability of winning just depends on how much money you have right now. It doesn't depend on at what time you have that money. Okay. So this is nothing but what? So this I just conditioned on an additional random variable st plus 1. I have to just uncondition it. So what should I do? What is the probability that I'll go to st plus 1 equal to s dash given st equal to s? I have to just multiply by that. Just like the previous one. Like here I conditioned on a and just wrote pi of a given s. Similarly, I conditioned on s dash. I just wrote p pi of s dash given s. Okay. So you have to be comfortable with this. You will come across this a lot. You just, if you want additional conditioning, you just take that conditioning and just multiply with the probability and sum over all possible values of that. Okay. You just condition on s dash, but you don't care what s dash is. So you just multiply the probability of s dash and just sum over all possible s dashes. Okay. We'll encounter this very frequently, so just be comfortable with it. Okay. So whatever additional conditioning you want to do, but just multiply with that probability and sum over all possible states. So this is what v pi of s equal to this. Now what is this last term? Is it equal to v pi of s dash? Why? What happened to the additional conditioning s? Because of Markov property. What gt plus 1 depends only on the future, right? Future returns and the future states that you go into. The future is independent of the past given the present. So st plus 1 is conditioned to be s dash. So what is st doesn't matter now. Okay. So what future returns you'll get only depends on where you are right now. So this will be equal to, due to the Markov property, that will be equal to due to Markov property. Okay. So is this clear? So this is what this equation is what is called Bellman expectation equation. Okay. So this is called so if you have some number of states, you have these are linear equations, right? Because all that you are doing is some multiplication and additions in this. So these are linear equations. So how many unknowns are there? What is our aim? To find v pi of s, right? You know the dynamics of the MDP. So by knowing the dynamics, I just for us it just means we know. Okay. Only those two matter for us. Like we might know the whole thing. We might know the joint distribution, but what really matters for us in whatever calculations we do is r pi r pi p pi ss dash. If you know the dynamics, you can calculate this. That means you know the dynamics of the MDP and you know what is policy pi. Now you want to understand how good is that policy. For finding that, you want to find what pi of s. So now we have derived some set of equations which v pi of s satisfies, right? So these are some set of linear equations. And how many unknowns are there? Number of states, right? Because for every state you have a V pi. So you have, let's say, n states, you have n unknowns. How many equations do we have? N equations. For every state we have one equation. So can we solve these equations? Are you are we always guaranteed to solve find the unknowns if you have n equations and n linear equations and n unknowns? Is it always guaranteed? So when is it guaranteed? Yeah, if you write it in y equal to h, like ax equal to b form, let's say, when, like, if we can write it as ax equal to b form, when are we guaranteed to have solution for this? None of the eigenvalues of matrix A should be 0, right? That is one condition you might have studied, right? If we can show that in no eigenvalue of A is equal to 0, that is the determinant is not equal to 0, then you can claim that there is a solution for this. There is a unique solution for this, right? Because you have n equations and n unknowns. We'll try to show that now. Or existence or uniqueness of the solution. So whether V pi can be solved with these linear equations is what we'll try to show. So can you write it in V pi equal to, like, Ax equal to B form? Can someone write it and tell me what will you get? So maybe you can just convert this into vector form. So V pi, you can think of it as a vector of, like, V pi of S1, so on, V pi of, let's say there are n states. You can think of it like this. You can think V pi as a vector which has all the state values. And you can also think P pi as a matrix. Okay. P pi of SS dash, right? For every pair of S and S dash, you have a value. So you can write it as a matrix, right? Where you have here state 1, 2, so on n. And here also you have state 1, 2, so on n. And P pi SS dash will, one particular value will give you P pi 1, 1. If you are in some state 1, what is the probability? You'll go to state 1 again if you follow policy pi. Is it clear? This notation is clear, right? So V pi is a vector of n cross 1. This is a matrix of n cross n if there are n states. Okay. So if you just try to write this using this notation, the vector set of equations will look the following: V pi equal to R pi. R pi also I'll write as a vector. Okay, because for every state I have a R pi of S. So R pi is also a column vector plus gamma times. You can verify that this will be equal to this. Okay. So this set of equations is nothing but this vector equation. Okay. B pi equal to R pi plus gamma into the matrix P pi into the vector V pi. Okay. You can just verify it. This is what we'll get. Now can we make it into Ax equal to B form? So what will it be? We'll get V pi equal to, if you just do it correctly, you'll get this. Okay. So I'm just clearing to get this form. Okay. Or this is like x equal to A inverse B. I just wrote it in that form. Okay. So just bring V pi to the left side and just take it. Okay. So I is the identity matrix. Okay. So now the question is whether this matrix is invertible or not. That's what we are interested in, right? if the matrix is invertible, then we are fine. So the way to argue this is the following. So we know we want to show that this matrix, all the eigenvalues of this matrix are non-zero. Okay. So like we'll just use some property of stochastic matrices. Like P pi is a matrix where each row will sum to one, right? Because what is a row in a P pi matrix? If you start from some state S, what is the probability that you'll go to state 1? What is the probability that you go to state 2? So on, what is the probability that you go to state n? So if you are in some state right now, next time slot, you'll be in some state or the other. So we just sum over all the probabilities in a particular row of P pi, that will be 1, right? Because you are in some state S, what is the probability that you'll go to state 1 in the next time slot? What is the probability that you'll go to state 2 in the next time slot? So if you sum over all those probabilities, that should be 1, because you have to go somewhere in the next state, right? So any matrix whose rows sum to 1, which is like where all the entries are positive and whose rows sum to 1, it's called a stochastic matrix. Okay. P pi has this property that every row sum to 1. Every row sums to 1. This is one property, and all entries are positive. This is one property. So any matrix which satisfies these two properties is called a stochastic matrix. Okay. So we'll just use some well-known property of a stochastic matrix, which says that the maximum eigenvalue of a stochastic matrix is at most 1. Okay. This is a property which we'll use. Like this is a fact which we'll use. Okay. If you take any stochastic matrix in the sense that all the entries are positive and each row sums to 1, then there's a well-known result which says that the maximum eigenvalue of this matrix is at most 1. Okay. So if we use this property, then we can just show that the maximum eigenvalue of matrix will be like every eigenvalue of that matrix is positive. We can just show that. Right? How we can show? Let's say instead of huh? Last one or this? No, you take any stochastic matrix, the maximum eigenvalue of that matrix will be at most 1. Okay. So now this is the matrix which we are interested in. So now I want to show that any eigenvalue of this matrix is non-negative, sorry, non-zero, right? So how do you find the eigenvalue of a matrix? So like you just if I just multiply any vector x, that will be equal to lambda x. So that's what we want, right? So this is equal to, so I'm just multiplying with some vector x. Now what will I get? Ix minus gamma p pi into h, right? And what is Ix equal to? X minus gamma p pi h. So how can I write it? P pi h is a vector, right? Because we multiply the matrix with a vector. So you can write it as 1 minus gamma p pi into x, right? So you got this into a form where x equal to lambda x. It's a scalar, right? Huh? H is a vector and P pi H is also a vector. So you're just summing two vectors which are multiplied by two scalars, 1 into X minus gamma into Y. Yeah, okay. Sorry, I just made some small mistake here. It's not P pi X, it's lambda. So it's P pi is a stochastic matrix, right? Uh, so any eigenvalue. So first we have to show something. Huh? Yeah. So I'm just understand. It's right. So this is one eigenvalue. Let this could be some arbitrary eigenvalue of P pi. If every eigenvalue of any eigenvalue of p pi is uh, less than 1, right? And if we choose gamma to be less than 1, then what can we say about this? Because gamma is less than 1 and lambda p pi is also less than 1. So 1 minus that will be positive. So if gamma is less than 1 and lambda p pi is less than 1 due to our fact, whatever we wrote here. Okay. So we are able to show that uh, any eigenvalue of this particular matrix is positive. So for every any lambda p pi is less than 1, right? So what is the question now? I'm just telling that any eigenvalue of this matrix is positive. What is the question? For every lambda pi p pi is a stochastic matrix. So any lambda p pi is less than 1, it will have a no, like for any matrix, constant. So, so that, that, that much is clear, right, in the first step. Otherwise, it won't be an eigenvector. So you take any eigenvector of that matrix, then you can write it in this form, right? For some particular for some lambda of p pi, and any lambda of p pi is less than 1. Is it still confusing? Okay. Like if X has to be an eigenvector of this matrix, it has to be an eigenvector of the other matrix, right? Otherwise, otherwise it won't be an eigenvector for this. Right? So maybe you have to argue that a little bit more carefully, but all that I'm saying is this is equal to I X. Otherwise, this is also an you won't get the overall thing as an eigenvector for that. So for some X to be an eigenvector of the first matrix, the other one looks like a necessary condition, right? So if you assume that, or I think it's even it can be argued, right? Because if you assume that X is not an eigenvector of p pi, then it cannot be an eigenvector for I minus gamma p pi. So if you take any eigenvector of the first matrix, that will be having this property. Is it clear to everyone, or is it confusing? Okay. So we are sure that you take any eigenvector of uh, that matrix which we are interested in, and we just calculated AH equal to lambda h kind of a thing, and we showed that lambda should be positive. That means it is non-zero. That means it is invertible, right? Because we showed that every eigenvalue of that matrix is positive. That in particular it is non-zero, so that matrix is invertible. So that means we'll have a set of equations. Is it clear? So we got some equations in V pi. We just argued that those equations are sufficient to get to solve V pi. Those are not some arbitrary equation. Those are some good equations which we can use to solve V pi. Okay. So implies V pi can be solved using Bellman optimality equation. So before I proceed further, is there any doubt in this particular part? Yeah. Okay. And V pi is also unique, right? Because we have n equations and unknowns and the matrix is invertible. So we have a unique V pi. Okay. Okay. So now we we know for a given policy pi and a given MDP dynamics, if someone asks you to find V pi, you know how to do, right? Unless the state space is, if the state space is very large, then inverting this matrix might be difficult, right? So we'll use some iterative algorithms to solve this problem. But mathematically, you know how to do it. You just calculate this matrix and you just calculate this I minus gamma p pi matrix and just take the inverse and just multiply with r pi. You'll get the v pi. Okay. So later we'll see, like due to the complexity in inverting this matrix, so we'll come up with some iterative algorithms to solve this inverse, to solve V pi. Okay. So before that, now we know how to find, how to evaluate the performance of a policy. V pi is telling how good a policy is, right? Now we have to understand what is the definition of an optimal policy first, and then how do we find pi star? That's our next question, right? So, how should we define an optimal policy? So, what is an optimal policy? What is a natural definition that comes? Pi star equal to argmax over pi v pi, right? Is it correct? Huh? Why minimum v pi is the expected return, right? Not the regret. Why minimum? No, I did not get you. No, you want a policy which will give you more return, right? So you just want the policy which has the maximum possible return. That's what we are trying to find. Since it's a vector, you are saying that. Is that what you're saying? Yeah, I'll come to that. So here, what is the V pi? V pi is what? The value of a particular policy, right? So let's say there are two policies. I'll say policy pi one gives me these. Let's say there are two states, S1 and S2, and I'll give you two policies. Maybe if you find the policy V pi for this policy pi one, maybe you get this. And let's say you find V pi for, let's say, another policy, you get something like this. Then what is the argmax for these two? Which policy is good? Huh? This is V pi 1, this is V pi 2. So pi 1 is a policy, pi 2 is another policy, and there are two states. And the first one is the performance of policy 1, the second one is the performance of policy 2. Now, if I ask which policy is good, what will you say? So there is no policy which is the best in every state, right? In state 1, the policy 1 looks good. In state 2, the policy 2 looks good. So let's say I want a policy which is the best in every state. Okay, that's how I'm going to define my optimal policy. Okay, I'm going to define a policy as optimal if that policy is the best policy in every possible state. Okay, so if there is another policy pi 3 which has, let's say, 11 and 13, then I'll call pi 3 as the optimal. Okay, if a policy is said to be optimal if it v pi of s is greater than any other policy for every state. Okay, so then a question comes whether such a policy exists or not, because it could be possible that, let's say, there are multiple policies and every policy has some vector like that v pi. It could be possible that all the vectors are like that, such that you cannot order them. You cannot order this vector is better, it is better, you cannot tell. If it is real number, you can tell. If I give you two real numbers, 5 and 6, you know 6 is greater than 5. But if I give you two vectors like this, you cannot always tell which vector is better than the other, right? It could be possible in some components one vector is better, in some components the other vector is better. So now the question is, if we define our policy, optimal policy, as the policy which has the best v pi in every possible state, that's how I'm going to define. Now there comes a question whether even such a policy exists. Okay, so there is a result which says that if you have finite number of states, if you have finite number of actions, and the rewards are bounded, that is, the rewards won't go to infinity. Okay, there is some number below which the rewards always lie below with some number. Then you can always show that there exists an optimal policy according to this definition. Okay, the definition is clear to everyone. A policy is said to be optimal if it is optimal for every state. Okay, and mm, then the question arises whether such an optimal policy even exists. Then I'm just giving you some sufficient conditions under which such an optimal policy always exists. Okay, so I'll call pi star. A policy pi is said to be optimal if it is it's if it's if it is the best if it has the best value in every possible state. Okay, now I am just giving you some sufficient conditions. So when will an optimal policy exist? So the answer to this is if you have finite number of states and finite number of actions, and your rewards are bounded. The expected rewards are bounded. Okay, and then we can if these three are sufficient conditions to guarantee the existence of an optimal policy. These three will guarantee you there exists an optimal policy. Okay, is this clear to everyone? You are able to appreciate, right? Why it could be possible that the policies are such that no policy is strictly better than other policy. So you might end up saying that there is no optimal policy for a given MDP. if we go with this definition. Like if you change the definition and say, let's say, instead of measuring the performance of a policy like a vector, you just take the average of that vector and say that is the performance of my policy, then always an optimal policy will exist. Like if not one optimal policy, there'll be multiple optimal policies, right? Because you are just comparing a real number. So instead of calling this as the performance, then every policy performance is a real number. Then you can compare real numbers and you can always say whichever policy has the highest real number, you call that as the best policy. Right now, since we are taking a vector as the performance of a policy, it is possible that there is no optimal policy at all. But under some conditions, we can always guarantee the existence of an optimal policy. So these are the conditions. Okay. In addition to that, these conditions also guarantee not just the existence of an optimal policy, it also guarantees that there exists a deterministic optimal policy. Okay. So in the sense that the optimal policy need not be a stochastic policy. There could be a deterministic policy which is optimal. Right? In the sense that when you are looking at this argmax over file, you have to search over all possible policies, right? So the policies could be stochastic policies also, which says that you play action 1 with some probability half, action 2 with some probability half. Now these conditions are saying that you need not search over all possible policies. You just search over policies which are deterministic. Which deterministic policies means what? For every action, for every state, it will give a particular action. Right? It's a mapping from state space to action space. We just look only at those mappings. Among those mappings, you will definitely find a policy which is optimal. Okay, and that policy will be better than any policy, not just deterministic policies. You just do the argmax over only deterministic policies. Whatever VPI you get, that will be the best VPI. Even if you look at all stochastic policies also, you won't get any better. Okay, so it's just saying that you need not search over all possible policies. You just search over deterministic policies. Your optimal policy will, at least there exists one deterministic policy which is optimal. Okay. There exists an optimal policy, and it also tells that 5 star, there exists a deterministic optimal policy. Okay. Is it clear? I see a lot of faces getting lost. Like, is it not clear? Something is not clear? No, I am for defining an optimal policy, you don't even need to talk about deterministic policy. I can define policy like first of all, if I care about only the optimal policy for a particular state, let's say I'm talking about some state S1. I just want to find what is the optimal policy for a state S1. So that performance can be measured by only one number, right? If let's say I care about only some state S. So then what is the performance of a policy on state S is a real number, right? So then I can define what is the best value that we can get for some state S. How can I write that? Argmax over all possible policies V pi of S. So this is, there is no ambiguity, right? It's not even talking about existence of a policy. Because you are talking only about one real number. Now for a given state, you can define V star of S like this. Now I'll just define V pi of S, like I'll call a policy optimal if V pi of S equal to V star of S for all S, then I'll call that policy optimal. So for every state, there is one maximum constant that can be achieved. So that's how all possible policies. You'll get what's called V star of S. Okay, which is the best policy, like the best value that you can give to that state. You do whatever you want. This, and if I'll define an optimal policy as V of S equal to V star of S. So maybe to make this thing a little bit clear, maybe let's look at an example. Yeah, yeah. It's not a policy like this. It's just a policy like this. This is a stochastic policy. This is a deterministic policy. Okay. So let's look at an example. Maybe it will be clearer. So let's say there is a grid like this, and our aim is to reach a particular goal state. Okay, and there is some agent which is put in one of these cells, and it has to reach this goal in the shortest possible path. Let's say the only actions that are allowed is left, right, up, down in a given cell. So let's say if an agent is here, then the only actions that will possibly is up, left, let's say. So if it takes some particular action, it will go into a next state, which is whatever cell it will lead it into. Okay. So here the states are, there are 25 states. Every square is like a state, and in every state there are four possible actions: left, right, up, and down. So, and let's say my MDP is like this. So the states the actions and I have to talk about rewards also, right? To specify it as an MDP. So if my aim is to find a policy which will go to the shortest path, what should be my reward? How should I define my reward so that reaching the goal in the shortest path will come out to be the optimal policy? No, that's not like before you talk about optimal policy, you talk about an MDP, right? You should talk about what are the states. If you want to define an MDP, what all should I define? I should define what are the states, what are the actions, and for every state and every action, what is the immediate reward that I'll get. I should tell these things, right? P pi SS dash I should tell, and R pi S also I should tell, right? So here P pi SS dash is like, let's say, deterministic transition. So if I take up, it will go to up cell with probability 1. If I take down, it will go to down cell with probability 1. Okay, that is my P pi. P pi is clear, right? You tell me any state, if not the P pi, we need to define PASS dash and RAS. This is what the MDP is, right? MDP doesn't give you any policy, right? What are the dynamics of the MDP? P of R S dash given S comma A. This is what the MDP dynamics, right? If you are in a state S and take action A, what is the probability that you'll go to some state S dash? These are the transition diagram. This is what gives us, right? This is what is specified by the transition diagram. If you have 5 rupees and if you get 2 rupees, what is the next state? With what probability you'll go to some state? That is what is defined by the MDP. And this is if you are in a state S and if you take action A, what is the expected reward that you'll get? Okay. So now I'll define PSS dash A like this. Like if I'm in some state S and if I take an action up, I'll go to the state above it with probability 1. If I'm in some state, if I take left, probability 1. For every other state, the probability is 0. Okay. This is clear, right, for everyone? There are 4 actions and I defined the probabilities like that. Whatever action you take, you go to that cell with probability 1. For every other state, the probability is 0. Okay. And RAS, how should I now? This is here now. States I defined, actions I defined the transition probability matrices. Then what else I should define? Rewards. So what reward will encourage me to go to the shortest path like go to the goal in the shortest path? If I'm in this state, for taking an up action, how much reward I should give? For taking a down action, how much reward I should give? For every state I have to tell, and for every action I have to tell. Right? Is there a simple way of defining this reward which will encourage me to go to the goal in the shortest path? Like I should define the reward in such a way that if I find the return from any state, the policy that gets the maximum return is nothing but the optimal policy, right? If you give the MDP definition, what will a optimal policy mean? The policy which will give you the maximum return, right? Maximum V pi of S. or maximum GT, right? So you should define it in such a way that the return will be the maximum for the shortest path. For any other path, the return should be lesser than the optimal path. Okay. So can you think of a simple way to assign these rewards? Hmm. So if you take what? So telling if it moves towards the goal, you give positive reward. If it moves away from the goal, you give negative reward. So that is like you are hard coding, right? You know where the goal is, and for every state, you are hard coding the reward. Can you do something better without knowing where the goal is? Can you define a reward which will still be valid? Like in the sense that if you follow the optimal path, you'll get the best return. If you follow any other path, you should get a slightly worse return. Is the problem clear? For optimal path, the return should be the best possible return. For every other path, the return should be slightly worse. Hmm. Till yeah. So that's a simple reward, right? You give -1 reward for any action in any state. So till when the episode will continue, you define this as the terminal state. You define this as the terminal state. Till you reach the terminal state, the episode will continue. What will be the total return for any path? Number of actions you took. So if you start here, you take this path, right, right. If you take this path, what will be your total return? -4, right? If you take any other path, the total return will be less than this, right? If you take, let's say, some paths, the total return will be some -7 or -6, right? Is it clear? So that's a simple way to define an MDP for this problem. Like the transition probabilities are deterministic in the sense that whatever action you take, you go to that state with probability 1. For every other state, it's 0. And the reward is -1 for any action in any state. In the terminal state, you won't take any action. You reach the terminal state, the game is over. Okay. Is it clear to everyone? Because if you assign a -1 reward for every action in any state, the shortest possible path will have the best possible return. So if you try to maximize the return over all possible policies, you'll get the shortest path as the optimal policy. Right? So now if we talk about the definition of optimal policy, let's think of it like this. So if I just care about like what is a policy, how can I draw a policy in this? Let's say I'm looking only at deterministic policies. So what are deterministic policies in this environment mean? For every state, I have to tell what action to take. That is a deterministic policy, right? Deterministic policy is a mapping from state space to action space. So if I put an arrow in every uh, state, like whatever arrow I keep, if I keep an arrow in every state, then the whole thing will specify one particular policy because it's a mapping from state space to action space. So action is the model by an arrow here. That's all, right? So if I care about only the optimal value of a particular state, if I care about only the value of a particular state, what will it be? So let's say I care about what is the value for this particular state. What is V by O? What is V star of S? What is V star of S for that particular state? What is the best return that you can get starting from that state? -2, right? So you just do this and then do this. So, but this is not the full policy, right? So what is the optimal policy if I talk about this? mixture of this is this particular state. And I talk about what is the maximum value that I can get from this state. So if I define my policy like this, so let's say I define my policy like this. Is this an optimal policy for that particular state? Is it an optimal policy for that particular state? Right? Because that particular state, the best return that you can get is -2. And this policy, correct? You start here and it will then and then it will move on from here. So the expected return for this policy, if you start from that state, is -2, which is nothing but V star of that state. Can any other policy give you better return than this for that state? No, right? So this is what I so look at all policies. Any policy give you the best value for the state is an optimal policy for that particular state. So for every state, there could be multiple optimal policies like this. So for this state, there are a lot of optimal policies. Right? So for every state, there will be a lot of optimal policies. So when do we call a policy to be optimal for the whole MDP? When for every state it is an optimal policy. So how can you find one such policy? So you just look at one state and you collect all the possible optimal policies for that state. So for this state, there are a lot of optimal policies, right? So you just collect all of them. Then you go to some other state. You collect all possible optimal policies for that state. So for every state, you go and collect the set of all optimal policies for that state. Then you just take an intersection of all of them. Okay? If the intersection is non-empty, then there exists an optimal policy for the whole MDP. Right? If there is some policy in the intersection of all these optimal policies for each state, that means that policy is the best policy in every possible state. That's how we are defining as our optimal policy. A policy which is optimal for every state. So now the question is, if you do like this, you go to some state S, you find all optimal policies for that state. You go to some other state S dash and find all optimal policies. Now you are taking an intersection of all these sets. Now the question arises whether the intersection will be non-empty. Because you are just collecting some sets and you are taking intersection, whether it will be non-empty. That's the question that will arise. Now we are saying that if the MDP has this property, then the set will be non-empty. Is it fine? Everyone understood what is an optimal policy? A policy which is optimal in every state. So you can, so this definition you understood, now you are able to appreciate this definition. So V star of S is R. So for every state there is some optimal value. Now you call policy optimal if V by of S is equal to V star of S for all. Okay. So for example, this policy is optimal. But it is satisfied this property? No, right? Because for some other state, this won't be a good policy. Okay. So these are the set of all deterministic policies. Now, what will be the set of all policies? If I don't talk about only deterministic policies, then what will be my set of all policies? I have to, every state, there are 4 possible actions. I have to put some probability on each action. So it's like 0.1, 0.4, 0.2, let's say 0.3, right? So for every, because every state I can take some action with some probability. So if you look at all possible policies, then you have to search over for every state 4 numbers, right? That is the set of all policies. Now this result is telling you need not search over all possible policies. You just search over deterministic policies. right? It is clear from this, right? Whether it is policy or whether it is a deterministic policy. Within deterministic policy, there is an optimal policy, right? Because you don't need a stochastic policy to get the best return here. Is it clear? So we know the optimal policy is just stay right appropriately, right? So for this MDP, we are seeing that there exists at least one deterministic policy which satisfies the optimal policy. That's what we are saying when I mean that there exists an optimal policy and also there exists a deterministic optimal policy. Like if this definition is telling, this definition is not telling something about deterministic policy. It is telling you to search over all possible policies. That means you have to search over even policies like this. Every state you have to tell me what probability should go up, what probability should go right, what probability should go left down. So now this, if these three conditions are satisfied, it is telling that you need not search over all possible policies. You just search over deterministic policy, but you'll still be able to get this star of S. B star of S can be achieved by just searching over deterministic policies. Okay. But this is very clear, right, from this example. In this example, if you just search over deterministic policies and find the optimal policy among them, there exists no other policy. Even if it's even if you come up with a stochastic policy, you cannot beat me, right? So that's what the meaning of that statement means. Okay. Yeah. So this is about the definition of optimal policy, and this is the regime which we'll look into. This for the initial part of the course, we'll assume these three conditions. That is, we know that there exists an optimal policy, and we also know that there exists a deterministic optimal policies. Now we need not search over all possible policies. We can just search over deterministic policies. So in the next class, we'll see how do we find one such optimal policy. We'll just search over deterministic policies and we'll find a way to find the optimal deterministic policy. Okay. Thanks.